Thank you for joining this introductory talk on quantum communications. First, I will present quantum technologies. These devices all use the properties of quantum mechanics to control and manipulate individual quantum systems, such as single atoms and photons. For example, in security, the company CryptoQuantic produced this advanced quantum security chip for IoT devices, which is almost impossible to hack, and it is currently being piloted in energy, defense, aerospace, and banking. And in sensors, we can reach the ultimate limits of precision in quantum physics. For example, when measuring the concentration of a blood protein by using optical interferometry and entangled photons in a microfluidic device. Analog quantum simulations can reproduce the behavior of real molecules like hydrogen. And quantum computers use quantum mechanical phenomena such as superposition and entanglement to perform computations. Now, last year, Google announced that it had achieved quantum supremacy. This means that its quantum computer is the first to perform a calculation that would be practically impossible for a classical computer. They estimated that a classical machine would take 10,000 years to complete this, even with 1 million processing units. And their quantum computer took just 200 seconds. By the start of 2019, private investors had funded at least 52 quantum technology companies. Most of them were university spinouts, and they had received $450 million in 2017 and 2018. This was more than 4 times the amount invested in the previous 2 years. Now, in order to talk about quantum communication, I'm first going to give a background in quantum mechanics, and I'll talk about how we use entanglement distribution to create these quantum networks, and I'll give a vision for the quantum internet. Now, in 2008, Jeff Kimball proposed the quantum network hardware needed to create a quantum internet. It consists of quantum nodes which are made from atoms, and they generate and store and process information. And these must be connected through quantum channels. And these channels use photons to transport the information between the nodes. Now, in our everyday lives, where objects are at a macroscopic level, they're large, we experience the world according to the laws of classical mechanics. However, at much smaller scales, for example, the sizes of atoms and electrons, the rules of quantum mechanics apply. The 3 main concepts of quantum mechanics are superposition, measurement, and entanglement. Superposition means that objects exist in many states at the same time. Qubits are the basic information unit in quantum information science. Classically, a bit encodes 1 state at a time, a 0 or a 1. A qubit, on the other hand, is a quantum 2-state system. For example, photon polarization. It can exist in both the horizontal and the vertical direction at the same time. Now, if you perform a measurement on this qubit, it collapses into one of these 2 states, 0 or 1, with the outcome a 0 or a 1 classical bit. Now, qubits can be created in such a way that they become entangled and it is no longer possible to describe the qubits independently, even when the particles are separated by a large distance. By measuring the state of one qubit, we influence the state of the other qubit. And entanglement is the most important resource for quantum communication. Because entangled qubits are not physically linked together, there is no way to intercept the communication between them. Now, quantum teleportation is a process to transfer an unknown quantum state from one particle to another at a distant location, without sending the original particle itself. Suppose Alice wants to securely communicate information to Bob, who is far away. Initially, they share a pair of entangled photons. So the entangled photon A goes to Alice and the entangled photon B goes to Bob. Now, Alice performs a special joint quantum measurement known as a Bell state measurement on her information qubit psi and her entangled photon or qubit A. This is a special measurement which only has one of 4 possible outcomes, and it gives you 2 classical bits of information. So Alice then communicates these 2 classical bits of information to Bob, and Bob performs a special operation on his qubit to recover the information qubit psi, Now, the information qubit no longer exists with Alice, but the state of this qubit has been teleported or transported to the qubit at Bob. Now, we recall that the quantum internet will consist of matter-based atomic nodes, and these will store and process the information, and they will be connected by photonic links to each other. So in order to create a quantum internet, we need to distribute entanglement between these nodes. And after that, we'll be able to teleport the information securely between the nodes. So I want to show you here an experiment that has been done recently to entangle light and matter over a distance of 50 kilometers of optical fiber. So a laser generates the entanglement between a trapped calcium ion qubit and a photon. And the photon has a wavelength of 854 nanometers. So they perform a photon conversion, so the wavelength becomes the telecommunication wavelength of 1,550 nanometers, and then it travels down the 50-kilometer fiber. And then when it's detected at the detection section, they measured that the light and the matter were still entangled. And so this just forms one part of what's needed to distribute entanglement between the nodes of a quantum internet. The next step of this experiment is to replicate this exact experiment and to generate entanglement at each of two nodes, A and B. And then the photons will travel between the nodes. Each will travel a distance of 50 kilometers. And where they intersect, a special measurement will cause the photons to become entangled. And now you have distributed the entanglement between two nodes over a distance of 100 kilometers. So if you imagine replicating this a number of times, you can start to think about building your quantum internet. And the distances of 100 kilometers become like real life distances that we consider between different cities, for example. So all of the quantum networks built today are called trusted node quantum networks. And they use a different protocol, different quantum communication protocol called quantum key distribution. So in this, you have a secure cryptographic key sent between two parties using quantum mechanical properties. Then they use these keys to encrypt messages which can be transmitted over a standard classical channel. However, in order to extend this protocol to long distances, you need the trusted nodes. For example, the quantum backbone was developed in 2016. It goes from Beijing to Shanghai in China and covers a distance of 2,000 kilometers. It uses 32 trusted nodes. If you had a network like this and it was a private network, for example, say a banking institute, you could see how that might work. However, if the government and the public are also going to be using such a network, everybody has to trust the nodes, and so it becomes less secure. The only true quantum network relies on establishing entanglement between the nodes, like I showed on the previous slide. And this is what groups in Europe are working towards. In the Netherlands, TU Delft came up with this. They established entanglement over a distance of 1.3 kilometers between two nodes. Now they want to extend this to 100 kilometers between four cities in the Netherlands: Amsterdam, Leiden, The Hague, and Delft. And they hope to achieve this by 2022. So on the bottom right here, you can see an image from a laboratory in QTech. This is just an example of one node in this experiment. And they have to replicate this in each of the cities. So it's very technologically challenging. Now, just to summarize the vision for the quantum internet. You imagine a quantum internet as a way of connecting quantum computers, simulators, and sensors via quantum networks and distributing information and resources securely worldwide. So they're expecting that this will become a reality by 2030. In Europe, the investment has been in the quantum flagship. It's 1 billion euros over 10 years, and they're basing most of their research on this entanglement quantum network. In the US, they have the Quantum Initiative Act, which is mostly concentrated on quantum computing and developing cryptographic standards. In China, their investment is in the National Laboratory for Quantum Information Science. And they're going to extend their quantum backbone network to reach the whole of China. So it will cover 35,000 kilometers, and it'll connect all the major cities. They're also going to complement this with satellite constellation quantum networks. So I haven't talked about their successful Messius satellite mission, where they demonstrated a number of different quantum communication tasks. But that'll be for another day. So I think Jerry's now going to talk about the applications and the projects that we're involved in. Thank you.
Thanks, Deirdre. I'm going to see if I can share my screen now. Okay. Is that visible to everybody?
Yeah.
Okay, so I'm going to start with some of the quantum research that we've engaged. So this is very nascent in TSSG. It's only gone on with the last year or so. So last year I was at a quantum internet hackathon in Trinity. Ireland were one of we were one of 6 European nodes. It was a pan-European hackathon. So it was the second quantum internet hackathon. The first one was last year in TU Delft, which, as you can tell from Deirdre's talk, is one of the pioneers in the quantum internet. So with 6 nodes, the Irish node was quite small, and as you can see from that image, that is the entirety of the participants in the Irish node. So it was limited. That said, we took a challenge on, and it was on QuantumKine, a QuantumKine implementation, and that has been submitted to the Irish Signals and Systems Conference this June, and it's a guide to implementing QuantumKine. Now, you can't fully implement QuantumKine because quantum memories don't exist, and that's one of the challenges that are there, but we've had a pretty good stab of putting the whole thing together. The QuantumKine it's an array of 4 classical bits. It's a rather large array of 4 classical bits, and everything there is I won't say unique, but there's such a strong array of it that ultimately they're all unique. It's actually based on a hitting matching problem, in this instance to a base 4, and a hitting matching problem is a classical problem as much as anything else. A simple example of a hitting matching problem is I could explain to you that I know your phone number, and I could tell you that if I added all the numbers up, they would equal X, and if I multiply them all together, they would equal Z. And you could do those calculations in your head, and you could figure out with reasonable level of certainty that I know your number or not. So I haven't told you that, we haven't shared your number information, we've just shared information about your number. And it's the same then with QuantumKines. You start picking out parts of the index and you say, I think it looks like this or it looks like that. Because it's base 4, it's very easy to convert it into 2 entangled qubits, which is nice and easy. And then because they have 2 entangled qubits, you effectively get this operation where you've no cloning. So as soon as you do a check on a coin, that proportion of the coin disappears because you've looked at it, you've collapsed the waveform. The paper is available if anyone wants more information on that. The other paper is a review paper that Deirdre and I have written. It's around quantum comms more specifically, and it's thrown up a lot of interesting problems for us to look at. So some of them are listed here. Deirdre was showing you their examples of shortwave or short-range optics at 854 nanometers and long-range optics at 1550 nanometers. So these are all standard telecom bands. So an interesting question is, can you have a fast tunable laser in a server provide you a quantum wavelength versus a standard classical wavelength? Can we do that in routers and switches and things like that as well? And again, Deirdre was explaining the issue of the distance, the decoherence problems that we're running into. So how do we build out those larger scale quantum networks with repeaters and stuff? Also that's there is another interesting one for me, at least, is can we get classical to quantum gateways? You know, so you might be able to get a full end-to-end quantum secured network, but can we do a gateway to break you into a classical network and break you back in again? There may be no point to that, but again, I suppose it's a question to ask at least. Collaborations. So we're collaborating, I suppose, internally and externally. We're signing an MOU with CIT, and this is around quantum comms, cybersecurity, Earth observation, Space 4.0. The benefit of this MOU and this collaboration is we're going to be funding and co-funding PhD students to work on quantum computing and CubeSats initially. Trinity or Connect have a quantum communications interest group, and there's a bunch of people there from Trinity, UCD, Maynooth, and ourselves involved with that. And then WIT, the School of Science. So we've been talking with people in the maths department because, again, quantum COIM is obviously a quantum algorithm rather than quantum comms. There's a lot of algorithmic stuff that is very interesting. We've also been talking to the optics research group, and we've been talking to some of the physicists as well, because, again, some of the fundamentals in quantum and quantum technology and quantum mechanics can be quite difficult to understand. Lastly, from a research and active research point of view, this testbed has arrived. It's in the data center, but it's not constructed. I got it just as the lockdown kicked in, and I haven't been able to put it together. But that equipment is there. It's a quantum key distribution demonstrator, and it can show you the effects of eavesdroppers, and it really shows you the polarization, the beam splitting, and things like that. Now, I have a ton more slides, but I'm not going to go through them. I'm only going to do one more slide on quantum communications and maybe one on quantum algorithms, and I'm going to leave it at that because time is getting tight. So Deirdre gave you a good introduction to quantum communications. Just, I suppose, really a few notes on some of the stuff that's there is quantum key distribution is the killer app for quantum comms. And that's come from one of the quantum algorithms, which is Shor's algorithm, which I'll discuss in a minute, which is kind of effectively show that the factorization of large numbers mightn't be a difficult problem anymore. A couple of other things that has come out of quantum communications is high dimensional entanglement, and this gives you qubits rather than qubits. So the initial work on quantum comms and qubits in particular was to take binary bits and make them quantum and give them quantum properties. Whereas when you look at quantum entanglement, when you look at information density in quantum, there's a lot more degrees of freedom in photons and in optics, and therefore you can have higher orders of higher bases, basically. So rather than it being base 2, it could be base 3, 4, 5, 6, and I think they've shown it to base 10 as it is. So that gives you a huge amount of information within a single photon, within a single item, and this gets very, very large, very, very fast, which is really nice. And another one that we have seen is quantum effects in biological systems, particularly around enhanced green fluorescent proteins. We've seen there's research papers out there where they have actually entangled those fluorescent, those photons coming from those fluorescent proteins. This is room temperature. That's room temperature entanglement. So that's a very unique thing, because most of what you would have seen previously, what Deirdre was describing, a lot of that is actually at a millikelvin, so it's barely it's not even 1 degree above absolute zero. Some of the limitations, and Deirdre talked about these already, is most of this network is still basically point-to-point links. It is expanding. Decoherence, which is effectively the length you can get on a single link, is quite short. Quantum repeaters are only really coming along, and they're very expensive technology-wise as much as anything else. And there are no quantum memories. You can't store entangled photons. They can be moving and passing, but they've no way of storing them, and that's where the problem kicks in with our quantum COIM. I suppose just one point on the quantum key distribution. It's effectively the equivalent of the HTTP protocol was to the internet. The internet was around for a long time, but it exploded once HTTP really came on the scene. I'm not going to go through all of these. I'm literally just going to do the first set of algorithms, and then I'm going to finish because I don't want to run us over time. So quantum computing on the algorithm side. So you've Shor's algorithm, which is a factorization algorithm. This is the most feared one, and it's what really has pushed on quantum key distribution. It's the impetus for nearly everybody getting involved in quantum computing. You've got Grover's algorithm. So quantum algorithms are effectively, they're expected to be polynomially faster than classical algorithms. Now, not all of them are. Grover's algorithm is quadratically faster, and some of the other ones are exponentially faster. So all of these are way faster, but the real benefits come sometimes in the polynomial faster algorithms. There's a bunch of different ones there. Quantum counting is an interesting one because that tells you the actual number of results you could have for a query or for an algorithm. So it's used as part of Grover's search algorithm because you might have whatever you're looking for, there could be 2 or 3 different answers to that search. And there's a bunch of hybrid algorithms as well. So they use a mix of classical and quantum in their algorithms. I'm going to stop here and leave it at that, but we have more slides and I'm happy to share the slides, and the rest of them are mainly around quantum computing.